There is a particle falling through your body right now. You did not consent to this. You cannot stop it. The universe does not care. It is called the Muon, and it should not be here. It forms high in the atmosphere and decays within 2 microseconds. The distance it needs to cover to reach you is far greater than anything traveling at its speed should survive. By every ordinary calculation, it dissolves long before the ground comes into view, and yet hundreds of them pass through every square centimetre of this planet every single minute, through rock, through lead, through you. That is the first strange thing. The second is its identity. The muon sits in the same fundamental family as the electron, same charge, nearly identical rules, except it is 200 times heavier. And unlike the electron, it does not last. Every muon that has ever existed has decayed into something else. Not one has survived. Nobody predicted it. Nobody needed it. When it was confirmed, the physicist Isidore Rabi had one response. Who ordered that? That is the correct reaction to something the universe made without being asked. So what is the muon really? Why does it have the mass it has? And why does something that shouldn't survive keep arriving anyway? If you like exploring questions like these, feel free to leave a like and subscribe. And if there is something about the universe you find yourself wondering about now and then, let us know in the comments. It might become the next question we explore. For now, let's get back to that question. The answer starts above the atmosphere, with a collision violent enough to tear matter apart and build something new from the wreckage. To understand where the muon comes from, you have to look up, not at the clouds, not at the weather, much further than that. Space is not empty. It looks empty from your window. It feels empty when you think about it at night, but it is constantly crossed by streams of high-energy particles moving at nearly the speed of light, protons mostly, some helium nuclei, some heavier fragments, all of them launched by some of the most violent events the universe produces: exploding stars, collapsing cores, regions around black holes where matter gets accelerated like nothing we can replicate in a laboratory. These particles travel enormous distances. Some of them have been moving through space for millions of years before they reach us, and they arrive here continuously, every second of every day, completely invisible to you as you make your morning coffee or sit in traffic or lie in bed, staring at the ceiling. We call them cosmic rays, which is one of those names that sounds dramatic but actually undersells it. These are not rays in any soft or gentle sense. They are particles carrying energies that dwarf anything produced in the most powerful accelerators ever built. When one of them hits the upper atmosphere, it does not pass through quietly. It hits the nucleus of an air molecule roughly 60 kilometers above your head, and that collision does not produce a small disturbance. It produces a cascade, a spray of new particles born entirely from the energy of that single impact. That cascade is where the muon's journey actually begins, not in a lab, not in a theory, in a violent collision above the clouds that you will never see and never feel. When a cosmic ray proton hits an air molecule 60 kilometers above your head, the collision does not behave like anything at human scale. Think about what a collision means in ordinary life. 2 cars meet on a road, metal bends, energy disperses. The cars are damaged, but they are still cars. The stuff that went in is roughly the stuff that comes out. Maybe some heat, maybe some sound, but no new cars spontaneously appear in the middle of the intersection. That is not how collisions work at the scale you live at. This is nothing like that. At these energies, the collision does not just damage the particles involved, it creates new ones, out of nothing but the energy of the impact itself. This is not a metaphor or a simplification. This is how particle physics actually works. Energy and mass are two expressions of the same thing. A collision violent enough will convert that energy directly into new matter. Particles that did not exist a moment before the impact simply appear. Born from the force of two things meeting at nearly the speed of light. What comes out of this collision is a spray of particles called pions. They are not fragments of the proton. They are not broken pieces of the air molecule. They are entirely new particles assembled from collision energy alone. If you were somehow floating up there watching it happen, it would look less like a crash and more like an explosion that manufactures its own debris from scratch. Pions come in three varieties: positively charged, negatively charged, and neutral. They spray outward from the collision point in all directions. A small, violent population of new matter appearing 60 kilometers above the surface of the Earth. And they carry enormous energy. They move fast, but fast does not mean stable. The moment a pion exists, its clock is already running. It has an extraordinarily short lifespan, far shorter even than the muon we are trying to understand. The neutral pions are the most impatient. They decay almost instantly into photons, pure light, gone before they travel any meaningful distance. The charged pions last slightly longer, a handful of nanoseconds under ordinary conditions, which sounds like nothing, and at human scale, it is nothing. But at these velocities, even a nanosecond covers real ground. Still, the charged pions do not survive long either. They decay, and what they decay into is not random. It is not a chaotic spray of whatever the universe feels like producing. The decay follows strict rules, rules that the universe appears to enforce without exception, every single time. And what comes out of that decay is the muon, not as a byproduct, not as a rare outcome, as the primary product, the thing the charged pion was always going to become, which immediately raises the next question. If the pion decays into the muon that quickly and that high up, then how does the muon ever make it down to the ground at all? So the charged pion exists for a handful of nanoseconds, and then becomes a muon. That part is straightforward enough. What is not straightforward is what that means for everything that follows. Let's put some numbers into this in a way that actually makes sense at human scale. A nanosecond is 1 billionth of a second. You blink and roughly 300 million nanoseconds have passed. The charged pion's lifespan is so short that if you lined up 1 billion pions end to end and watched them all decay in sequence, you still would not have waited long enough to finish a single breath. And yet, that brief existence is enough. Because the pion is moving at a significant fraction of the speed of light, and at those speeds, even a lifespan measured in nanoseconds covers a meaningful distance before the clock runs out. But here is what matters more than the pion's journey. It is what the pion leaves behind when it goes. When a charged pion decays, it does not simply vanish. It converts. The energy and mass it carried reorganize into new particles according to rules the universe does not bend. A positively charged pion becomes a positively charged muon and a neutrino. A negatively charged pion becomes a negatively charged muon and an antineutrino. Every time, without exception. The muon takes the majority of the energy. It inherits the pion's velocity, and it immediately begins its own countdown. Now, the muon is the one with a clock running, and its situation looks even worse than the pion's. The muon's lifespan is about 2 microseconds, 2 millionths of a second, which sounds like an improvement over the pion until you do the distance calculation. Light travels about 600 meters in 2 microseconds. The muon moves slightly slower than light, so in its entire lifespan it should cover somewhere around that distance before decaying. Maybe a little more, certainly not much, but it needs to travel 60 kilometers to reach the ground. That is 100 times further than its lifespan should allow. If you drove 60 kilometers from your house and your car was only allowed to run for 600 meters before the engine permanently shut off, you would not make it out of your street. The muon should not make it out of the upper atmosphere, and this is where the chain stops making sense by ordinary rules. Because the muon does make it, reliably, in enormous numbers. Something is allowing it to cover a distance its own clock says is impossible. That something is not a loophole, it is not an exception. It is one of the deepest results in all of physics operating exactly as it should. Let's stay with the muon at the moment it appears. Right at that instant when the pion converts and the muon takes its place in the chain, it inherits everything. The velocity, the direction, the enormous kinetic energy the pion was carrying from the original collision 60 kilometers above. The muon arrives already moving at roughly 98% of the speed of light, pointed downward, toward the ground, toward you. At human scale, that velocity is genuinely difficult to picture. The fastest thing most people have ever been inside is a commercial aircraft that moves at roughly 900 kilometers per hour. The muon moves at roughly 1 billion kilometers per hour. That is faster in a way that belongs to an entirely different category of motion. A category where the ordinary rules of time and distance start to behave in ways that feel wrong, but turn out to be perfectly consistent with how the universe actually works. This is the muon's defining situation from the moment it exists. It carries a lifespan of 2 microseconds, and it moves at a speed where the physics of time itself begins to shift. That shift is invisible from the outside. You would see nothing unusual watching it happen, but the mathematics underneath are doing something that changes everything about how far this particle can travel before it dies. The muon also carries charge, the same magnitude as an electron, and that charge means it interacts with matter. It responds to electromagnetic fields. It can be deflected, it can be measured, it leaves a trace in anything sensitive enough to record it. That trace is actually how we know any of this. The muon was discovered by noticing something in a detector that had no business being there. A signal arriving from above with properties that match nothing in the existing catalogue. It had mass and charge, and it was coming from the sky, and it was decaying into something else before anyone could do much more than confirm it had arrived at all. What made the discovery genuinely difficult was not the detection, it was the acceptance. The assumption kept being that what they were seeing must fit somewhere familiar, that it must be something already named and understood showing up in an unusual way. It took years before the physics community accepted that what they were looking at was a new kind of particle entirely, one that sat in the same family as the electron but was heavier and unstable, and had apparently shown up without any theoretical invitation. I find that part quietly fascinating, because it says something true about how discovery actually works. The new thing arrives and the first instinct is always to make it old again, to find the category it belongs to file it away. The muon resisted that. It kept not fitting. And eventually the only honest response was to accept that the universe had produced something nobody had asked for and nobody fully understood. But accepting that it exists is only the beginning. The deeper question is how it gets here at all, and that answer lives inside something the muon is doing to time on its way down. The muon should not reach the ground. Every calculation based on its lifespan says it decays long before it gets here, and yet it arrives in enormous numbers, so something has to give. Either the lifespan is wrong, or the distance is wrong, or time itself is not behaving the way it does when you check your watch in the morning. It is the third one. When an object moves at a significant fraction of the speed of light, time does not pass for it at the same rate it passes for you. This is not a quirk of measurement. It is not an illusion produced by the distance between observer and particle. It is a genuine physical difference in how much time elapses. The muon's internal clock runs slower than yours, not because something is broken, because that is what velocity does to time at these scales. From your position on the ground, the muon's 2 microsecond lifespan stretches, not because the muon is doing anything special, but because it is moving so fast that time itself dilates around it. The faster an object moves, the slower its clock runs relative to a stationary observer. At 98% of the speed of light, that effect is substantial. The muon's lifespan as measured from the ground is not 2 microseconds. It is closer to 14, long enough to cover 60 kilometers, long enough to reach you. This is worth sitting with for a moment, because it is easy to hear and immediately file away as an interesting fact without letting it land properly. The muon does not survive because of some biological trick or some material property that makes it resistant to decay. It survives because time runs differently for things moving at these speeds. The universe is not bending a rule for the muon. The universe is following its rules exactly. And those rules say that time is not a fixed backdrop. It is a physical quantity that responds to motion. You experience a version of this yourself. If you have ever flown on a long international flight, your clock ran very slightly slower than the clocks of people who stayed on the ground. The difference is too small to notice without atomic precision instruments. But it is real. It has been measured. The physics that keeps the muon alive long enough to reach your feet is the same physics, just operating at a scale where the effect becomes impossible to ignore. And this is where the muon stops being just a curiosity from high-energy physics and starts being a proof. A physical demonstration arriving continuously from the sky. That time is not what it feels like from the inside of a human life. So the muon survives the descent. Time dilation stretches its clock just enough to cover the distance. It arrives at the surface moving at nearly the speed of light, and it is still intact, still charged, still carrying the energy it inherited from the Pions 60 kilometers above. And then it hits something. At sea level, the muon does not find empty space. It finds atmosphere. It finds buildings. It finds the ground. It finds you. And here is where its charge becomes relevant in a very concrete way. A charged particle moving through matter interacts with the electrons in the atoms it passes through. Not violently, not in the way the original cosmic ray proton hit the air molecule and tore everything apart. Gently, a long, continuous series of small electromagnetic nudges, each one taking a tiny amount of energy away from the muon as it passes through. Think of it like walking through a crowded room. You're not stopped by any single person, but every slight brush of a shoulder slows you down just a little. By the time you reach the other side of the room, you are moving noticeably slower than when you entered. The muon experiences something like this as it passes through matter, except the room it is walking through is rock, or concrete, or the floors of your building, or you. Dense material takes more energy from the muon than thin material. A muon passing through a mountain loses significantly more energy than one passing through open air. Some muons slow down enough that they stop entirely and decay wherever they happen to be. Others retain enough energy to keep going, to pass through everything in their path, and continue downward until the clock finally runs out. The ones that reach you at sea level are the survivors. They started with enough energy and enough velocity that even after 60 kilometers of atmosphere and whatever structures happen to sit above you, they still have momentum, they still have charge, they are still muons right up until the microsecond they are not. This continuous rain of survivors is not a trickle, Roughly 10,000 muons pass through a square meter of horizontal surface at sea level every minute, through every roof, every floor, every body sitting in every chair in every building on the surface of this planet, right now, without pause, and every single one of them is already dying. Every muon that reaches the surface is running out of time, not in a metaphorical sense, in a precise, measurable physical sense. The clock started the moment the pion converted, and it has been running ever since. By the time the muon reaches sea level, most of that clock is already gone. 2 microseconds is the average, but average is doing a lot of work in that sentence. The muon does not have a fixed expiration point the way a parking meter runs out at an exact time. Its decay is probabilistic. What the 2 microsecond figure tells you is that if you gathered an enormous population of muons and watched them all simultaneously, roughly half of them would be gone within that window. The other half would persist a little longer, some significantly longer, a few almost embarrassingly longer than expected. This is not unique to the muon. It is how all unstable particles behave, and it is worth understanding because it connects to something deeper than just the muon's lifespan. It connects to why decay happens at all. The muon decays because it is not the lowest energy state available to it. Physics has a strong preference for lower energy configurations. A ball sitting on a slope will roll downward if given the chance. The muon is sitting on a slope. It has more mass than the particles it can become, and mass is energy. So the universe is always applying a kind of pressure on the muon to convert into something lighter. What it converts into is specific. A muon does not decay into arbitrary particles. It decays into an electron and 2 neutrinos. 1 muon neutrino and 1 electron antineutrino. Every time. The charge is conserved. The energy is conserved. The identities of the products are fixed by rules that do not bend. That electron carries away most of the energy. The 2 neutrinos carry away the rest, and the muon simply ceases to be a muon. The thing that was falling through the atmosphere and passing through rock and nudging electrons aside as it went is gone, replaced in an instant by 3 lighter things moving in slightly different directions. What is remarkable is not that this happens. What is remarkable is how precisely it happens. The products are always the same. The rules are always followed. And those rules point towards something the muon is embedded in that goes much deeper than the particle itself. When the muon decays into an electron and 2 neutrinos, something is being preserved that is not immediately obvious from just watching the products appear. It is not just charge. Charge conservation is the easy one. The muon carries a negative charge, and the electron it produces carries a negative charge. The 2 neutrinos carry no charge at all. The books balance, and that is not surprising. Charge conservation is one of the most firmly established rules in all of physics, and nothing in the muon's decay violates it. What is more subtle is the conservation of something called Lepton number, and understanding this requires stepping back for a moment and looking at the broader family the muon belongs to. Particles in physics are divided into 2 broad camps based on how they behave. On one side, you have quarks. Quarks are the particles that make up protons and neutrons. They interact via the strong nuclear force. They cluster together. They form the dense cores of atoms. On the other side, you have leptons. Leptons do not feel the strong nuclear force at all. They are in a sense more solitary. They do not bind into composite structures the way quarks do. They exist as individuals. The electron is a lepton. The muon is a lepton. The neutrino is a lepton. And there is a rule that governs all of them. The total lepton number of any interaction must remain constant. You cannot create a lepton without also creating an antilepton. You cannot destroy a lepton without also destroying an anti-lepton. The universe keeps a running count, and it never lets that count change. This is why the muon's decay produces exactly the particles it does. A muon has a lepton number of +1. When it decays, that lepton number has to go somewhere. The electron it produces also has a lepton number of +1, but the muon was specifically a muon. It belonged to a specific branch of the lepton family, and that branch has its own separate lepton number that also has to be conserved. So the decay produces a muon neutrino to carry the muon lepton number forward, and because an electron has appeared where there was no electron before, the universe also requires an electron antineutrino to balance that creation. 3 particles, each one appearing for a specific reason, rooted in conservation laws that operate at every scale and in every interaction without a single known exception. This level of bookkeeping is not bureaucratic. It is structural. It tells you that the muon is not just a particle with a short lifespan. It is a node in a network of conservation rules that connect it to every other lepton that has ever existed. Its decay is not a collapse. It is a transformation that preserves every quantity the universe considers worth preserving. And the fact that the muon has its own separate lepton number, its own dedicated conservation rule, its own distinct identity within the lepton family, that is not a technical detail. That is the first real clue that the muon is not an accident or an anomaly. It is a member of a structure with a very specific shape, and that shape is about to become the most important thing in this entire chain. The muon reaches the surface and it does not stop. That is the first thing to understand. It does not land, it does not settle, it does not interact with the ground the way a raindrop does, or the way a gust of wind presses against a wall. It passes through. And the reason it passes through tells you something fundamental about the structure of matter itself. To understand why the muon penetrates so deeply, you have to think about what matter actually is at small scales. An atom is almost entirely empty space. The nucleus sitting at the center is extraordinarily small relative to the overall size of the atom. If you scaled a hydrogen atom up to the size of a large sports stadium, the nucleus would be roughly the size of a marble sitting at the center of the field. Everything else is the electron cloud, a diffuse probabilistic region where the electron is likely to be found, but where there is no solid substance in any conventional sense. When a particle passes through matter, it is mostly passing through that emptiness. The question is what it interacts with along the way, and the answer depends entirely on what forces the incoming particle responds to. The original cosmic ray proton that started this whole chain interacted strongly when it hit the atmosphere. It felt the strong nuclear force. It got close enough to an atomic nucleus to trigger a violent interaction and produce the pion cascade. That is what the strong force does. It operates at extremely short ranges, but when something gets within that range, the interaction is powerful enough to completely restructure what was there. The muon does not feel the strong nuclear force at all. It is a lepton. Leptons are simply not wired for that interaction. The strong force is invisible to them in the same way that a radio signal is invisible to something that has no antenna. The muon passes through atomic nuclei without triggering that kind of violent restructuring. It gets close, it goes past. Nothing catastrophic happens. What the muon does interact with is the electromagnetic force. It carries charge, and as it moves through matter, it passes close to the electrons orbiting the atoms in its path. Each of those encounters produces a small electromagnetic interaction, a tiny transfer of energy. The muon nudges an electron slightly, loses a small amount of its own energy in the process, and continues. This is called ionization. The muon deposits energy in thin, continuous threads through whatever material it crosses, through air, through water, through the tissue in your body, through concrete and steel and rock. The thread is narrow, and the energy deposited per unit length is small enough that it causes no meaningful damage to biological material at typical muon fluxes. You are being ionized right now in the most literal sense, and you are completely unaware of it. The depth a muon penetrates depends on how much energy it started with. A high-energy muon can pass through hundreds of meters of rock before losing enough energy to stop. The ones arriving at sea level from cosmic ray cascades carry enough energy to pass through you entirely and continue into the ground beneath your feet without pausing. This penetrating power is actually one of the muon's most practically useful properties, because something that passes through dense matter while leaving a faint ionization trail can be used as a kind of natural imaging tool. Physicists and engineers have used muon tomography to image the interiors of volcanoes, to scan the internal chambers of ancient pyramids, to inspect nuclear reactor cores and cargo containers without dismantling them. The same property that makes the muon seem ghostly turns out to make it extraordinarily useful as a probe. But the penetrating power is a consequence of identity. The muon passes through matter so readily because of what it is, because of the forces it responds to and the forces it ignores. And that identity connects directly to a question that has not been answered yet. Why does a particle with these exact properties exist at all? Why this mass? Why this charge? Why this specific set of interactions, and not some other combination entirely? The muon has a mass of roughly 106 mega-electron volts. That number will not mean much on its own, so let's put it in context. The electron has a mass of roughly half a mega-electron volt. The muon is about 207 times heavier. Not 2 times, not 10 times, 207 times. For a particle that behaves in almost every other respect identically to the electron, that mass difference is not a small variation. It is a chasm, and nobody knows why. That is not a rhetorical pause for effect. It is a genuine statement of the current situation in physics. The mass of the muon is a measured quantity that the standard model of particle physics accepts as an input. It does not derive it, it does not explain it, it does not produce it from any deeper principle. The mass is simply there, and the theory absorbs it the way a spreadsheet absorbs a number you type into a cell. It stores the value and uses it correctly in every calculation, but it offers no explanation for why that cell contains 106 instead of something else. This is deeply uncomfortable if you think about it carefully. Physics has been extraordinarily successful at finding the reasons behind things. The charge of the electron follows from the structure of quantum electrodynamics. The masses of protons and neutrons emerge from the binding energy of the quarks inside them. There are derivations, there are mechanisms, there are reasons. The muon's mass has none of that. It sits in the theory as a free parameter, a number that has to be put in by hand because nothing inside the theory generates it from first principles. The same is true for the electron mass, and for the tau mass, and for the masses of the quarks. The standard model is in this sense less a complete explanation of matter, and more a precise accounting system that requires you to fill in certain values from experiment before it can tell you anything useful. What makes the muon's mass particularly striking is the scale of the gap. If the muon were just slightly heavier than the electron, you might imagine it was the electron in a mildly excited state, a small perturbation, something that could be explained by a minor difference in how the particle sits within some underlying field. But 207 times heavier is not a perturbation. It is a completely different regime. The muon and the electron behave identically under the electromagnetic force and identically under the weak force, and yet one of them is 207 times more massive than the other, for no reason that current physics can articulate. There is a name for this discomfort. Physicists call it the flavor problem, or sometimes the mass hierarchy problem. The question of why the three generations of matter particles have the masses they have, with no apparent pattern and no known underlying mechanism. The muon sits right at the heart of that problem. It is the middle child of the Lepton family, heavier than the electron, lighter than the tau, separated from both by ratios that have resisted every attempt at explanation. Some physicists have spent entire careers trying to find a pattern in the mass ratios of the fundamental particles, looking for a formula that generates the electron mass and the muon mass and the tau mass from some deeper input. So far, nothing has worked. The numbers remain stubbornly arbitrary, which either means the pattern is hidden behind physics we have not yet found, or something more unsettling, that the masses are what they are because of processes that occurred in the early universe that selected these values without any deeper necessity behind them. Either way, the muon's mass is one of the most prominent open questions sitting inside an otherwise extraordinarily successful theory. It is not a loose end in an obscure corner. It is a gap right in the middle of everything. The muon does not stand alone in this. That is what makes the mass problem more than just a curiosity about one particle. It is part of a pattern that runs through the entire architecture of matter. When physicists mapped out the fundamental particles over the course of the 20th century, they expected to find a minimal set, the smallest possible collection of building blocks that could account for everything observed, and for a while it looked like that was exactly what they had. The electron, a handful of quarks, the neutrino, a small clean catalogue of ingredients that seemed to be enough to build everything in the universe, from atoms to stars to you. Then the muon arrived, and then more particles arrived after it, and when the dust settled, what physicists found was not a minimal set. What they found was that the catalogue repeated itself 3 times. Every particle in the first generation has a heavier counterpart in the second generation, and every particle in the second generation has an even heavier counterpart in the third. The electron has the muon and the tau. The up quark has the charm quark and the top quark. The down quark has the strange quark and the bottom quark. Each neutrino comes in 3 flavors matching its charged lepton partner. 3 complete copies of the same basic structure. Each copy heavier than the one before. Each copy unstable except for the lightest members of the first generation. The proton is stable because it is built from first generation quarks. The electron is stable because there is nothing lighter for it to decay into. Everything in the second and third generations eventually cascades down into first generation particles. The muon decays into an electron. The heavier quarks decay into lighter ones. The universe at low energies is made almost entirely of first generation matter, which raises an immediate question. Why 3, not 2? Not 7, not 1, 3. The standard model does not answer this. It accommodates 3 generations because experiment demands it, but it provides no mechanism that requires exactly 3 and forbids a 4th. There is no known principle that says the repetition stops where it stops. Physicists have searched for 4th generation particles and found no evidence for them. But the absence of evidence is not the same as a theoretical proof that they cannot exist. Some approaches to physics beyond the standard model do make predictions about the number of generations. Certain constraints from cosmology, suggest that the number of light neutrino species is very close to 3, which indirectly constrains the number of generations if you assume each generation comes with a light neutrino. But these are observational constraints. They are not derivations from first principles. They tell you what the number appears to be. They do not tell you why. The 3-generation structure is one of the deepest unexplained features of the Standard Model. It is not a detail. It is not a footnote. It is a central organizational feature of all matter that the most successful theory in the history of physics simply accepts without explanation. The muon exists because the 2nd generation exists. The 2nd generation exists because matter comes in 3 copies. And why matter comes in 3 copies is a question that remains genuinely open. What is not open is the consequence of that structure, because the repetition of generations is not random variation. It follows a pattern, and that pattern points directly toward one of the deepest organizing principles in all of physics. The 3-generation structure is not just a curiosity about how many particle types exist. It points towards something that runs much deeper through the foundations of physics. Something that connects the existence of the muon to one of the most powerful organizing principles the universe appears to follow. That principle is symmetry. And in physics, symmetry does not mean what it means when you look at a butterfly or a snowflake. It means something more precise and more consequential. A symmetry in physics is a transformation you can apply to a system that leaves the underlying laws unchanged. Rotate the universe by any angle, and the laws of physics still hold. Move everything 1 meter to the left, and the laws of physics still hold. These are symmetries, and wherever a symmetry exists, a conservation law follows. That connection between symmetry and conservation is one of the most profound results in all of theoretical physics, and it governs everything from the way light behaves to the way particles decay. The Standard Model is built almost entirely on symmetry. The forces themselves emerge from symmetries. The electromagnetic force arises from a symmetry related to the phase of quantum fields. The weak force and the strong force arise from more complex symmetries of the same general type. The particle content of the theory is not chosen arbitrarily. It is constrained by the requirement that the whole structure remain consistent under these symmetry operations. And here is where the generations become more than just a head count. The 3-generation structure is connected to a deep requirement of mathematical consistency within the theory. If you try to build a version of the Standard Model with certain numbers of generations, the mathematical machinery that underlies it develops what physicists call anomalies, internal inconsistencies where quantities that should cancel each other out fail to do so. The theory breaks down. It stops being self-consistent. The cancellation of these anomalies requires a precise balance between the quarks and the leptons in each generation. The muon is not optional within this structure. Remove it, and the 2nd generation becomes anomalous. The mathematical consistency of the theory requires that if the 2nd generation quarks exist, then the muon and its neutrino must also exist. The muon is not an extra. It is a required component of a structure that has to balance. This is a remarkable thing to sit with. The muon exists not because some process happened to produce it, and it survived. It exists because the mathematical architecture of the theory that describes all of matter and all of the forces demands it. Take out the muon, and you do not get a simpler theory. You get a broken one. That does not answer why there are 3 generations rather than 1 or 5. But it does mean that within each generation the particle content is not arbitrary. It is fixed by consistency requirements that have no wiggle room. The universe is not decorating itself with extra particles for aesthetic reasons. It is satisfying constraints that run all the way down to the mathematical foundations of how forces and matter are allowed to interact. The muon is necessary. The question is necessary for what? And the answer to that lives one layer deeper still. So the muon is a required component of a mathematically consistent theory. Its existence is not optional. The structure demands it. But the structure does not demand that it weigh what it weighs. And that gap between what the theory requires and what the theory explains is where one of the deepest unsolved problems in physics lives. The masses of the fundamental particles span an extraordinary range. The top quark is the heaviest known fundamental particle. It weighs roughly 350,000 times more than the electron. The neutrinos are so light that measuring their masses precisely took decades of effort and still leaves significant uncertainty. Between the lightest and heaviest fundamental particles, the mass range covers at least 11 orders of magnitude, 11 powers of 10. If you scaled that range up to human sizes, it would be the difference between a single grain of sand and a mountain range. Within the Lepton family alone, the spread is severe. The electron sits at roughly half a mega-electron volt, the muon at 106, the tau at approximately 1777. No known principle generates these three numbers from a common source. No equation in the standard model looks at some deeper input and produces all three as outputs. They are measured, they are entered, they are used, but they are not explained. Physicists have tried for decades to find a pattern. In the 1980s, a researcher named Yoshio Koide noticed something striking. The three charged lepton masses satisfy a numerical relation with a precision that goes well beyond what you would expect from coincidence. The relation is simple enough to write down in a single line, and it holds to better than 1 part in 10,000 across the measured values. It has been verified repeatedly as measurements improved, and yet nobody knows why it is true. It has no derivation from any accepted theory. It sits there as a precise numerical fact about the universe that current physics cannot account for. This is the kind of thing that keeps certain physicists awake at night. Not because it is alarming in a practical sense, but because a relation that precise and that simple usually means something. In the history of physics, when a clean numerical pattern appeared in data, it often pointed toward a deeper structure waiting to be found. The orbital periods of planets followed a pattern that pointed toward gravitational mechanics. The spectral lines of hydrogen followed a pattern that pointed toward quantum mechanics. A clean relation among the lepton masses could be pointing toward something, or it could be a coincidence that happens to hold at current measurement precision and breaks down once instruments improve. Both possibilities are uncomfortable in different ways. What makes the mass hierarchy problem more than just a numerical puzzle is what it implies about the Higgs field. The masses of fundamental particles in the standard model arise from their interaction with the Higgs field. A particle's mass is determined by the strength of its coupling to that field. The electron couples weakly, the muon couples more strongly, the tau more strongly still. But the theory provides no mechanism that sets those coupling strengths. They are free parameters, numbers the universe chose and the theory accepts without question. Understanding why the muon couples to the Higgs field with exactly the strength it does would mean understanding something about the Higgs field itself that current physics does not capture. It would mean finding the layer beneath the standard model where these couplings are not inputs but outputs, where they are derived rather than assumed. That layer has not been found. Every experiment designed to probe it has so far returned results consistent with the standard model and nothing more. The muon's mass is not a solved problem wearing the costume of an open question. It is a genuine gap, a place where the most successful physical theory ever constructed reaches the edge of what it can explain and stops. There is one place where the muon has been measured so precisely that the gap between theory and experiment becomes visible as a number, not as a philosophical discomfort or an abstract admission that something is unexplained, as a concrete measurable discrepancy that sits at the frontier of modern physics and refuses to go away. Every charged particle with spin behaves like a tiny magnet. It has a magnetic moment, a quantity that describes how strongly it responds to an external magnetic field. For a simple point particle with no internal structure and no interactions beyond the bare minimum, the theory predicts a magnetic moment of exactly 2. That baseline value follows directly from the basic equations of quantum mechanics, and it is exact. But particles do not exist in isolation. They exist inside a quantum field that is never truly empty. The vacuum of space at the quantum level is not a blank absence of anything. It is a seething background of virtual particles, pairs of particles and antiparticles that flicker in and out of existence on timescales too short to observe directly. These virtual particles interact with the muon as it moves through the field. They nudge its magnetic moment away from the baseline value of 2. The difference between the actual magnetic moment and the baseline value is called the anomalous magnetic moment, and calculating it requires accounting for every possible virtual particle interaction that could contribute. For the electron, this calculation has been performed to extraordinary precision, and the agreement between theory and experiment is among the tightest in all of science. The electron's anomalous magnetic moment is known to better than 1 part in a trillion. Theory and experiment match at that level. It is one of the great triumphs of quantum electrodynamics. The muon is heavier, and because it is heavier, it is more sensitive to contributions from virtual particles with high masses. Particles that are too heavy to affect the electron's magnetic moment in any detectable way can leave a measurable fingerprint on the muons. This makes the muon's anomalous magnetic moment a uniquely powerful probe. If there are particles or fields beyond the standard model that have not yet been directly detected, their virtual contributions would show up here. The muon's magnetic moment is in this sense a window into physics that might exist beyond what we can currently see. And for decades, the measured value of the muon's anomalous magnetic moment has not matched the theoretical prediction, not by a catastrophic amount, but by enough to be statistically significant. The discrepancy sits at roughly 4 standard deviations from the predicted value depending on which theoretical calculation you use. 4 standard deviations is the kind of gap that in most areas of science would be considered strong evidence that something is wrong with the theory or missing from it. The experiment that produced the most precise measurement ran at Fermilab outside Chicago. It used a storage ring roughly 14 meters across to keep muons circling in a precisely controlled magnetic field. As the muons circled, their spin precessed at a rate determined by their magnetic moment. Measuring that precession rate to extraordinary precision gave a value for the magnetic moment that persistently sits above what the standard model predicts. I find this particular result one of the most quietly compelling things in contemporary physics, because it is not a dramatic anomaly in some exotic high-energy collision. It is a precise measurement of a property of a particle that falls through your body every day. And that measurement is telling us that the standard model is not the complete picture, that something is contributing to the muon's magnetic behavior that the theory does not account for. Whether that something is a new particle, a new field, a new force, or something nobody has thought of yet remains genuinely unknown. The muon arrived without being asked, and now it is pointing at something the universe has not yet shown us. Everything the muon does comes back to two numbers, its mass and its charge. The mass determines how it is made, how long it survives, what it decays into, how it sits within the generation structure, how sensitive it is to virtual particle contributions. The charge determines how it moves through the world, how it interacts with matter, how it can be detected, how it responds to fields. These two properties between them account for nearly everything the muon is and does, but charge in particular deserves a closer look, because the muon does not just happen to carry the same charge as the electron, it carries exactly the same charge. Not approximately, not within some measured tolerance, exactly. To every decimal place that has ever been measured, the charge of the muon and the charge of the electron are identical, and that identity is not explained by the standard model in any deep sense. It is observed, it is assumed, it is built into the theory as a given, but nobody has derived it from a more fundamental principle. This matters more than it might seem. The universe contains positive and negative charges in almost perfect balance. The proton carries a positive charge that cancels the electron's negative charge to extraordinary precision. If that balance were off by even a tiny fraction, the electromagnetic repulsion between like charges would overwhelm gravity at large scales, and the universe as we know it would not hold together. Galaxies would not form, stars would not ignite, you would not exist. The fact that the proton's charge and the electron's charge cancel so precisely is itself an unexplained feature of the standard model. The proton is built from quarks, the electron is a lepton. They are completely different kinds of particles governed by different forces with different internal structures. There is no obvious reason their charges should balance so precisely, and yet they do, and the muon carries that same charge. Exactly. Some extensions of the standard model attempt to explain this charge quantization through a deeper unification. Grand unified theories propose that at extremely high energies, the separate forces of the standard model merge into a single force with a single symmetry. In that unified picture, the quarks and leptons are not separate families. They are different aspects of the same underlying structure, and the charge relationships between them follow necessarily from the symmetry of that structure, rather than being put in by hand. If something like that is true, then the muon's charge is not a coincidence and not an assumption. It is a consequence, a necessary output of a deeper symmetry that the standard model is only an approximation of. The muon would be carrying that charge not because the universe happened to make it that way, but because the underlying structure of matter at the deepest level requires it. That deeper structure has not been confirmed experimentally. Grand unified theories make predictions that include proton decay at a rate that experiments have so far not observed, which either means the unification scale is higher than current experiments can probe, or the specific theoretical frameworks being tested are wrong. But the motivation for seeking that deeper layer is real, and the muon's exact charge is one of the signposts pointing toward it. There is something worth pausing on here. The muon has been treated throughout this entire chain as an anomaly, as something unexpected, as the particle nobody ordered, and in one sense that framing is correct. Its existence was not predicted, its mass is not explained, its generation structure has no known origin. The discrepancy in its magnetic moment points at physics beyond what we understand. But in another sense, the muon is one of the most precisely understood objects in the universe. Its charge is known exactly. Its decay products are fixed without exception. Its interactions follow rules that have held without a single violation across every experiment ever performed. It is simultaneously one of the most mysterious and one of the most precisely characterized things in all of nature. That combination is what makes it so valuable. The gaps in our understanding of the muon are not gaps in noisy data. They are gaps that show up against a background of extraordinary precision, and gaps that precise are the ones most likely to point somewhere real. The muon interacts with matter, but not all interactions are equal, and the difference in how strongly the muon couples to various forces compared to other particles is not a minor technical footnote. It is one of the most structurally important facts about what the muon is. Start with the electromagnetic force. The muon couples to it with exactly the same strength as the electron, same charge, same electromagnetic interaction. If you put a muon and an electron in identical magnetic fields, they deflect by amounts that differ only because of their mass difference. The underlying coupling is identical. This is why the muon behaves so much like a heavy electron in most electromagnetic contexts. The force sees them the same way. Now consider the weak force. The muon couples to the weak force as well. This is the force responsible for radioactive decay. It is the force that drives the muon's own decay into an electron and two neutrinos. And here again, the coupling strength is the same as the electrons. The weak force does not distinguish between the muon and the electron in terms of how strongly it pulls on them. They are treated as identical by both of the forces that govern their behavior. This is called Lepton universality, the idea that all charged leptons couple to the electromagnetic and weak forces with the same strength regardless of their mass. It is a prediction of the Standard Model, and it has been tested with extraordinary precision across decades of experiments. Every test has confirmed it. The muon and the electron are genuinely interchangeable from the perspective of these two forces. Mass is the only thing that sets them apart, which makes the mass difference even harder to explain. If the forces treat them identically, then the mass cannot be coming from some difference in how the particle sits within the force structure. It has to be coming from something else entirely, from the Higgs coupling, from whatever sets the strength of that coupling, from a layer of physics that the force structure itself gives no hint of. But Lepton universality has also become one of the most carefully watched quantities in modern particle physics, because if it ever breaks down, if a precision measurement ever finds that the muon couples to the weak force at a slightly different strength than the electron, that would be a direct signal of physics beyond the Standard Model, a crack in one of the foundational assumptions the theory is built on. Recent measurements of certain rare particle decays involving the muon have at various points suggested possible deviations from Lepton universality. Some of those hints have faded as more data arrived. Others remain under active investigation. The muon is once again at the center of the question, behaving almost exactly as the theory predicts. Almost. And that almost is where the next layer of physics may be waiting. The muon has been falling through you this entire time, while you have been listening to this, while the chain has been descending from cosmic ray to pion to muon to decay, to generation structure to symmetry to mass hierarchy to magnetic anomaly. Hundreds of them, through the ceiling, through you, through the floor, gone before any individual one could be named, and the universe has offered no explanation for any of it, not for the mass, not for the 3 generations, not for the precise charge, not for the magnetic discrepancy. The muon arrives, it passes through, it decays into an electron and 2 neutrinos that disperse in different directions and carry with them every conserved quantity the universe insists on preserving. and then it is over. The muon that fell through you a moment ago is already gone, converted into something lighter, something the theory predicted with precision, something whose existence raises no new questions. The muon itself raised every question. What I keep returning to is the Rabi response. Who ordered that? It was said with the exasperation of someone who had just been handed a complication they did not ask for. But looked at from where we are now, it reads differently. Because the muon turned out not to be a complication, it turned out to be a signal, a particle the universe produced without being asked, that has spent the decades since its discovery pointing insistently at the parts of physics that are not finished. The mass hierarchy, the generation structure, the anomalous magnetic moment, the charge quantization. Every unresolved question the muon carries is a place where the map runs out, where the theory that has successfully described every experiment performed in the last 50 years reaches a boundary and stops explaining. The muon did not create those boundaries. It revealed them, and it keeps revealing them with every precise measurement that returns a number the standard model cannot derive from first principles. There is a version of this that could feel unsatisfying. We descended through 18 layers of mechanism and arrived at a set of open questions rather than a closed answer. The muon exists because the pion decays, and the pion exists because cosmic rays hit the atmosphere, and the muon survives because time dilates and it decays, because it is not the lowest energy state, and its mass is what it is, because the Higgs coupling is what it is, and nobody knows why the Higgs coupling is what it is. But I do not find that unsatisfying. I find it the most honest possible answer to the question we started with. What is the muon, and why does the universe bother making it? The universe bothers making it because the mathematical structure of matter requires it, because the second generation cannot exist without it, because the theory would be internally inconsistent without a particle sitting exactly where the muon sits. The universe does not make the muon carelessly, it makes it necessarily. Why it weighs what it weighs, why there are 3 generations and not 2 or 4, what is causing the magnetic moment to sit just above the predicted value. Those questions are still open, and they are open not because physics has failed, but because the muon is precise enough and well understood enough that the gaps show up clearly against the background of everything that is known. That is what the muon is, not a loose end, not an anomaly that will eventually be explained away. A precisely characterized object sitting at the intersection of everything the standard model can explain and everything it cannot, falling through you continuously, carrying questions the universe has not answered yet, and leaving just enough of a trace to let us know that the questions are real.